I'll begin with a word of prayer. Dearly Father, we thank you for this day. We thank you for the weekend and for the nice weather. And I just pray that you'd bless this class, help us to use the time wisely to glorify you what we do. And also just pray that we'd have a productive break, restful, and just to you be glorified in whatever we do, Lord. In your name I pray. Amen. Okay, so to get straight to it. Today we're talking about normal subgroups. And so we'll pick up a few really interesting theorems in this section. So let me just restate the definition for us again. Definition: a subgroup H of a group G is called normal. All right. If GH is equal to HG for all G in G, we denote this by, we denote normality of H by H. Now, the book doesn't bother with the little dash under the triangle, but I tend to. It's not written in stone. You don't have to write it. If you don't want to, if you rather write the triangle, it's fine with me. Okay? So, let's see here. Get the perfunctory examples out of the way. Example 1. Well, how about the group itself, right? Or the trivial subgroup. Think about it. It's pretty obvious that G and 1 are going to be normal subgroups of G. Right? It's not hard to see that. Example 2, if G is abelian, right, then, you know, if you calculate GH, so that's going to be what? GH such that H is an H, right? And if it's abelian, that's literally HG such that H is an H, which is HG, right? But G being arbitrary, that shows that an arbitrary subgroup of an abelian group is normal. So normality in abelian groups is kind of boring. Perhaps a less boring example, example 3, and I kind of stumbled into this the other class. If we look at S3, which is what? 1 sigma squared, tau sigma squared, and you can use epsilon there if you want. I'm going to use 1, like 1. 1's nice. Well, if you look at the subgroup generated by sigma, in fact, you can show that that's a normal subgroup of S3. The best reason to see that is because it has index 2. We'll talk about that more a little bit later in the lecture, so let me not get into that too much. But on the other hand, the subgroup generated by tau, right? What is that? Not tau, but tau sigma maybe? Trying to remember. Oh, tau will do just nicely. Why am I making it more complicated? This is what we looked at, tau. Of course, that's got 1 and tau in it, right? So what's the left coset by sigma? Sigma tau, right? Which is equal to sigma tau sigma squared. On the other hand, if we look at the subgroup multiplied by sigma, the right coset of sigma with this subgroup, we've got ourselves, you know, sigma and tau sigma, which of course is not equal to the other one, right? So therefore, tau is not normal subgroup of S3 if even if there's any pair of cosets left and right which don't agree for a given representative, then game over, not normal. All right. Example 4. You can easily prove that the center of a group is a normal subgroup of G, right? So if you, if you look at x times the center of G, this is almost the same calculation. What is this? This is xg such that what? G is in ZG, right? What does it mean for G to be in ZG? Commutes with everything in G. So in particular, it commutes with X. Right? Oh, there it is. But X is arbitrary. So that shows you that the left and right cosets of the center match. In fact, that's exactly my example too. Just qualifier is a little bit different, but calculation is basically the same. So the center of a group gives you a normal subgroup, right? You notice that normal subgroups don't have to be found inside the center. I mean, like if you remember, the center of S3 was what? It was just 1, and so like if the center's not, I mean, here's a subgroup. The subgroup generated by sigma is inside S3, but it's not inside the center of S3, is it? And yet it's normal. Okay, anyway, theorem 3. And the things that this theorem say are sometimes taken as the definition of normality. So here it is. Let H be subgroup of G, the following are equivalent. 1, H is a normal subgroup of G. 2, G, H, G inverse is a subset of H for all G and G. 3, equality. G, H, G inverse is equal to H for all G and G. So these are so-called normality conditions, normality tests, and any one of these would make the one would be a kind of vacuous definition of normality, right? It's kind of somewhat self-referential, probably bad. But certainly 2 or 3 are viable candidates for the definition. In fact, grown-up group theorists don't really think of normality in terms of left and right cosets being equal. This is actually a very awkward characterization of normality, truth be told. Really, when you get into it, more interesting questions, almost always we use 2 to check normality. So let's look at the proof there. I won't do the whole thing. I'll just try to do the proof of 1 implies 2 here. Partial proof, I'll leave the rest to you guys. Okay, so suppose that H is a normal subgroup of G, right? Let G be an element of G, right? Then, of course, we have that HG is equal to GH, right? By normality. Let's let X be an element of G inverse HG. What's my goal then? I want to show that that is actually necessarily an element of H. If I can do that, that shows that the conjugation of H by G, that conjugate subgroup, is necessarily a subset of H, which is what I want. All right. So to say this, thus, X is equal to G inverse HG for some H and H, right? But the thing is, this is equal to G inverse, right? GH2, as HG is an element of HG that's equal to GH, right? Implies that HG is an element of GH, which is to say that there exists H2 in H such that HG is equal to GH2. I cannot say that HG is equal to GH. That's not what equality of these cosets gives me, right? It gives me the existence of some other element H2 which commutes with G. I have equality of the sets. I don't have equality of the elements necessarily, all right? So I have to run through this idea. I can commute G and H, but not quite. I have to trade it for a different element of H, according to the definition of coset. But then, what's this? That's H2, right? And H2 is an H, right? So therefore, X is an element of H, and we find that G in GHG inverse is a subset of H. And that one implies two.
Well, we proved G inverse HG, but those would be equivalent, right? Because we make an arbitrary HG.
What did I do? Oh, come on. Did I do that?
Did it work out the way?
Did I do that? Fine, let me fix it. Well, okay, fine. Yeah, you're right. So I've proved this, haven't I? So let Pac-Man be an element of G, and Pac-Man inverse equals to G. Then Pac-Man inverse H, Pac-Man is a subset of H, right? Which is to say, G inverse is a subset of H. I mean, I can apply, the point is I can apply this part of the proof to Pac-Man, right? The larger point is this: if this holds for an arbitrary group element, it holds for the inverse of that element as well. I'm still not convinced, Sam.
Well, I mean, there's no Pac-Man on both sides.
Yeah, you should just have an inverse.
Did I do it again?
The second Pac-Man should have
Yeah, I wanted the inverse over here, didn't I? Sorry. I'm determined to put that inverse on the wrong side, aren't I?
Or both sides.
Or both sides. All right, we're going to move on because this is not important. Well, I mean, it's important, but what we're getting into at the moment is not. I guess I can, fine. I'd rather not fix it. I'll let you fix it. Should I fix it? I don't know. I wish this had been pointed out about 3 minutes ago. Fine, GHG inverse. There we go. I will start again. Here we go. So X in there. I do it right? Yeah, I got it. Okay. So that means what? X is equal to GHG inverse for some H and H, right? But this is equal to GG inverse times H2, as HG inverse is equal to G inverse H by normality of H. The thing is, I also have left and right cosets are matching for G inverse. So it's pretty much the same argument, of course, but there we go. I fixed it. corollary, if G is generated by X, some subset, then H is a normal subgroup of G, if and only if X, H, X inverse is a subset of H for all X in the generating set X. So, in particular, most interesting case for us, I suppose, in particular, the normal subgroup generated by A is that's a subgroup of G if and only if G inverse is an element of the cyclic subgroup generated by A for all G and G. Okay. Proof. Homework. All right. Now, let's see here. We should talk about this. So, look at number 2 of this theorem 3. What does that say in terms of inner automorphisms? Like, remember what sigma G of X is? What was it? It was Gx G inverse, right? So how could we restate 2? I mean, 2 is really saying what? It's really saying that sigma G of H, right, is a subset of H, right? In fact, if you believe 3, which we haven't proved, but you can, it's not that hard. I mean, this is 3, right? 3 would give you that, not for any G, but for all G, right? What does this mean in words? So this means that the inner automorphisms of G fix H. H is sent to itself under conjugation by every inner automorphism if it's a normal subgroup. So this leads to a definition, a slightly more greedy thing. Definition: if sigma of H is equal to H for all sigma in aught G, then H is so-called characteristic subgroup. So that's greedier, right? Because there generally are outer automorphisms which are not inner. There can be automorphisms which are not conjugation, right? Conjugation is a special kind of automorphism. It's an inner automorphism. Generally, there's more out there. If your subgroup is fixed by the full automorphism group, then it's said to be a characteristic subgroup. These are even more special than the normal subgroups. You notice that every characteristic subgroup would be normal, right? Because the inner automorphisms are automatically automorphisms. But the converse isn't necessarily true. There could be normal subgroups which are not fixed by some outer automorphism. In fact, this is addressed in Nicholson in exercise 24, part C, in this section. This is an example, which is really nice. I like this example a lot. In fact, this example and the theorem which follows are really maybe my favorite part of this section. Example 4 of section 2.8. Here we look at G equal to GL2. And honestly, folks, I mean, I'm following him. So, fine. I mean, 2 by 2 matrices, great. Was that the camera? I mean, if somebody took a picture, it's cool.
Yeah, it sounded like it was.
Oh, that's weird. Maybe the projector just like died. the dying gasp of the projector. Let's hear. See, you know, I'm sorry, it bothers me. Like, why put a 2 here? There's nothing, there's literally nothing to do with 2 by 2 matrices in this example. It's so stupid. I mean, what does he think? It's like less scary to the students if, whoa. Whoa. So, I mean, I don't know why he's got n equals 2 in this example. It's just silly. See, because basically the whole calculation here is, the argument is that this is a normal subgroup. Let me show you why. So if we look at A, B, A inverse, right? This would be, and so let B be an element of SLN, which is what? Determinant 1, right? So this just means that the determinant of B is 1, right? This means what? Right, determinant not 0. So if we look at A inverse B, did I do it again? I keep doing this. I tell you what, A, B, A inverse, there we go. Just please give me at the start of the example, not the end. Otherwise I regret my life. So this is, if we look at the determinant of this guy, well, you know how it goes. Determinant A, determinant B, determinant of A inverse, but by linear algebra these guys cancel, and we're just left with determinant of B, which is 1, right? So what's this show? This shows that A, SLN, R, A inverse is a subset of SLN, R for all A in GLN R, which is to say what? The special linear group of n by n matrices is in fact a normal subgroup of the general linear group of n by n matrices. You notice almost every single example we work, I don't know, I say just, you know, you probably should make 2 the definition. I don't know. Okay, so theorem. This theorem is really nice. Theorem, it's nice to use, it's nice to remember, it's just nice. 4 of section 2.8 simply says this: if H is a subgroup of G with index 2. Oh man, I just erased it. It was right here. There was one right here, had index 2, which is how I knew it was normal. The one generated by sigma, that has index 2 because it's size 3 in a 6th order group, which means there's 2 cosets, has index 2. Then H is a normal subgroup of G. So the proof here is really, really, really simple. If you let G be an element, G be an element of H, then what? Clearly GH is equal to H is equal to HG, right? What's the other possibility? G is not an element of H, right? Thus, HG is not equal to H, right? But by our discussion the other day, we have G is what? It's the disjoint union of H and HG. But you know what you can do for the left, you can do for the right. So it's also equal to the disjoint union of H and GH. But by set theory, this implies what? Which is to say that, so HG is equal to GH in all possible cases, consequently, H is normal. So index 2, normal. there are wonderful applications to this theorem. Applications of theorem 4. How about AN? AN, if we look at SN, what's the index of AN and SN? It's 2, right? AN has order n factorial divided by 2, the alternating group. So it's an index, it has index 2. Consequently, AN is a normal subgroup of SN by theorem 4. Also, if you look at the dihedral group of order n, and you look at the subgroup generated by its cyclic, its element, you know, I'm saying dn is a, b, such that the order of a is n, the order of b is 2, and ABA equals b. I should just say ab equals 1. Oh well, anyway, there's it. Oh, my, need to make up my mind here. There we go. So that A, that cyclic subgroup, how big is it? By our work in the cyclic group section, we have a element of order n, generates a cyclic subgroup with n distinct elements, right? I mean, brackets A has order n. How many things are in Dn? 2n. How many cosets for A? 2. Index is 2. So that says that this is a normal subgroup of the dihedral group. Of course, you probably could calculate both of these and show, you know, that the same is true by element-wise consideration, but I think this is much preferred. Okay, so the remainder of lecture concerns a series of results that lead us to the concept of a simple group. So I think what I'll do here is just get into it. Lemma 1. Lemma 1. If H is a normal subgroup of G, and if K is a normal subgroup of G, with the intersection of H and K just being 1, all right, then we get what you guys want. We get that HK is equal to KH for all H in H and K in K. And the proof of this is just, it's a very neat, slick, really fun proof here. So here's the proof. Let's let H be in H and K be in K, all right? And by the way, this is the thing he doesn't say in this section. Throughout this whole arc of the section, he keeps saying, let HK, let KH, blah, 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 be in blah, blah, blah. He never comes out and tells you that H must be in H and K must be in K. But this is a convention we're going to insist on for the rest of this lecture, and you should understand in the book. When he writes H, it's from H. When he writes K, it's from K. He doesn't actually say it, but the notation assumes this to avoid writing about 50 sentences in this part of the section. H is in H, K is in K, H is in H, K is in K. About the 500th time you write it, you'll regret it. So, but I wrote it. Here it is. I did it once. So X equals to, here's the thing, HK, I want to say H inverse, K inverse. So it's just a matter of interpretation, guys. So on the one hand, we can write this as HK, H inverse, parentheses, K inverse, right? On the other hand, we can write this as HK, H inverse, K inverse, parentheses, right? Notice that this is what? This is an element of HK, H inverse, which is equal to what? K. Oh, I'm sorry. I can't do. If I somehow messed this up. HK, H inverse, HK, H inverse K. Yeah, that's fine. I'm just somehow confused. I don't know what's wrong with me. Oh yeah. Okay, that's the point is this is an element of K, right? On the other hand, over here, this is an element of K, H, K inverse, right? Which by normality of H is equal to H, part 3 of the normality test. So in parentheses, that's an element of H. So X on the one hand is a product of elements of K, but X on the other hand is a product of elements of H. So this implies that X is an element of K and X is an element of H. Therefore, X is an element of H intersect K, which implies, of course, which is equal to 1, right? By assumption. So therefore, X is equal to 1. But what does it mean for X to be equal to 1? Yeah, right. So 1 equals to HK. H inverse K inverse implies that HK is equal to KH. But these were arbitrary elements picked from H, picked from K, which shows you if we have normality of two subgroups, right, and we have that their intersection is trivial, we do in fact get pairwise commutation of the elements. Aha, I see you there. Lemma 1. So let's think about it. What's the significance of H intersect K? What is H intersect K as it relates to H and K? The largest what? Subgroup of G contained in what? Both H and K, right? And then you may recall earlier we also had a little discussion, maybe I didn't have it in here, but it certainly was in the book. If we look at the union of two subgroups, that's not usually a subgroup, right? The only way that can end up being a subgroup is kind of the stupid case that one is a subset of the other, right? Then like the union is just either H or it's G, so it's either H or K, so it's a subgroup, right? So this is the what? This is the smallest subset of G containing what? Both H and K, right? And usually, it's not a subgroup. But, and this is also not a subgroup, but here's a natural candidate for being a subgroup that contains the union, right? The so-called product, HK. It's just what you'd think it is. It's HK, such that H is in H and K is in K. The rest of the section is mostly devoted to studying when this is a group and how to kind of rip it apart. It's not always a group. There's an example in S3 given. I'll let you look at. I guess we could look at it. So if we look at H, so like non-example, HK not a subgroup of G for H equal to, I guess this is a useful use of a minute here, K equals to epsilon tau sigma. What's the product of H and K equal to then? You guys help me out with that. See, I'll start out easy. It's definitely got epsilon. It's definitely got tau. It's got tau sigma. What else has it got? Why? How does it have sigma? Oh, tau times tau sigma. So it's got sigma, right? Anything else? How would it get that? That's not in here, though. So there you go. So apparently that's it. And of course, this is not a subgroup of S3. So it doesn't have to be a subgroup, but it can be. When can it be? Well, that's lemma 2. Lemma 2. The following are equivalent for H and K subgroups of G. 1, HK subgroup of G. 2, HK equals to KH. And the very dumb, but for some reason pedagogically necessary, KH subgroup of G. Okay. I mean, like, by symmetry, 3 follows from 1 and 2, right? I mean, yeah. So we don't really need to prove 3. It's kind of like automatic from relabeling. Let's try to prove 1 implies 2, okay? All right, so what do? We assume that HK is a subgroup of G. And our goal is to show we're going to let HK be an element of HK. All right. So that's a let that somehow degenerated into a la. Sorry about that. So of course, if this is a subgroup of G, then we have that HK inverse is an element of HK, right? This goes under inversion, which implies what? K inverse H inverse is an element. Well, that's K inverse. I'm getting lost in here. I'm sorry. Let me regroup here. I don't think that's. I think I'm chasing a rabbit here. I don't have enough time to chase rabbits today. Where was I? All right. Fine. I write these notes for a reason. Let me look at them. Well, that was kind of it. Oh, I see. What? Oh. All right, then K inverse H inverse. What's confused me is I've tried to do the opposite order as what I wrote in the notes. Then K inverse H inverse is equal to what? It's equal to HK inverse, right? Which is an element of HK, which implies that there exists H1, K1 in HK such that what? K inverse H inverse is equal to H1, K1. And then you can invert this. This gives me that KHK is equal to K1 inverse H1 inverse, right? Which is an element of what? This is in K. This is in H. So we're looking at an element of KH. So this, to get from here to here, invert. So that shows, so far I've showed what? Therefore, HK is a subset of KH. So pick, let's see here, KH, an element of KH, then what? That's equal to, KH is equal to H inverse, K inverse, inverse, which is an element of what? See, this is an element in HK inverted. So by the fact that HK is given to be a subgroup, this is an element of HK. Right? So that implies that KH, well, that implies, of course, that KH is a subset of HK, which shows you that they're equal.
Or we could just get it by relabeling our first result.
Yeah, I think so.
Do we need that whole thing for the first half of that, or can we just do the same thing that you did on the second part? for the first half?
I would rather not speculate on simplifications of the proof at the moment. It's almost hard to tell in here when he's, I don't know. I just, I'm not sure. 2 implies 1. Let me just check time here before I commit to that. I'm going to leave you guys. That brings us to theorem 5. It's not more difficult than what we just did. It's just details, but it's more important I get you to the punchline here, I think. So I'll be going sans, well, I'm not sure if I have time for more proofs here. It's theorem 5 of section 2.8. Let H and K be subgroups of G, then 1. If H or K is normal, then HK equals to KH is a subgroup of G. All right? 2, if both H and K are normal, then guess what? HK is a normal subgroup of G. It's theorem 5. The proof is not difficult. I'm going to move on to theorem 6 here. Theorem 6, if H is, we actually get to some really useful calculational things here, so I'll make sure that I have time to say them to you today because I think they're really neat and worth having in our arsenal of things to calculate with. H is the normal subgroup of G, and K is the normal subgroup of G with intersection trivial, all right? Then look at this. HK is isomorphic to H cross K, where that's the Cartesian product of the subgroups. I will talk about the proof of this a little bit. So first, HK is a subgroup of G by theorem what? By theorem 5. You see, if H and K are both normal, then theorem 5 gives me that it's a subgroup. Then you can define sigma from H cross K to HK, all right, by sigma of HK equals to HK. I'll just tell you what happens. You can get sigma is 1 to 1 from lemma 2. It's actually that lemma 2 that ends up, oh, wait a minute, lemma 1, I think, actually is what ends up doing it for you. It's this, this thing here somehow. Anyway, I'll just do the homomorphism property. So if we have sigma of H1, H1 comma K1, H2 comma K2, right? That's sigma of H1, H2, K1, K2, right? By definition of the operation in the direct product. And so that's equal to H1, H2, K1, K2. But then here's where that lemma 2 comes into, lemma 1 comes into play in particular. See, we can commute the, and we got H1, K1, H2, K2, but hey, that's exactly sigma of H1, K1, sigma of H2, K2, and there you go, that's the homomorphism property. Homomorphism property basically follows from lemma 1, and I'll leave the rest of the details to you guys, but this is like super nice. Getting to the point here. So, I can find a marker that works. This has corollaries. Corollary 1 is that if G is a finite subgroup, finite group, and you have subgroups H and K that intersect to be 1, then the product of the orders of the subgroups is the product of the order of the product. So corollary 1 basically says that HK is equal to this for G finite. And we're also assuming, of course, that H intersect K is equal to 1. Corollary 2 says that if we have G finite, if we have H and K both normal, all right, if we have that the intersection of the subgroups is 1, and if we have that the product of the orders of the subgroups is equal to the order of the group. If you have all of this, then you get that G is isomorphic to H cross K. And then example 7 is basically just a straightforward application of corollary 2. It says if the greatest common divisor of M and N is 1, and if you have G cyclic, and the order of G is Mn, all right, then G is isomorphic to Cm cross Cn. This is huge. Example 8 is also really nice, but I'll let you read it, or if you want to see me talk about it, I'll talk about it tomorrow, I guess. So, sorry I didn't have time for proofs of all of these, but the proofs are very similar to what I've already shown you. And let's just apply this for a second. So what good is this for? Suppose you have Z, I don't know, 39, right? What's this isomorphic to? Right, this is isomorphic to Z3 cross Z13, yeah. And if you work out the details of this, example 7, it even gives a prescription for finding the generators of these subpieces. So what's the generator of Z39? 2, right? So like Z3 is isomorphic to, I believe, 2 to the 13, and Z13 is isomorphic to the oh, I'm sorry. I'm supposed to do, what world am I in, right? 13 times 2, yeah? Sorry. And 3 times 2. But anyway, I'll try to get into this more detail tomorrow. I'll show you some examples of it or whatever. But if you don't want to come, you don't need to come, of course. If you want to watch it, you can watch it. If you don't want to watch it, you don't have to watch it. Have a good break. Oh, man.